Good afternoon, everyone. Thank you for attending our webinar. This is part 2 of the Private LTE network, the technical dive. We had a webinar a couple weeks ago, and this is the second part of the webinar. So what I would like to do is introduce you to Jeff Broderick, who's with CTIconnect, and he can go over a little bit about CTIconnect before we move into the presentation.
Thanks, Sue. My name is Jeff Broderick. As Sue said, I've been with CTIconnect for about, it's approaching 6 years now. Been in the industry for about 20. I'm really excited with where we're going with things, and it's my honor to introduce the webinar today, Private LTE Networks, the deep dive into technical. And just a little bit about CTIconnect. We've been in the market since '95, primarily with wireless ISPs, but we also serve a whole bunch of other types of folks. We are part of the Convergent Technologies family of companies, which I'll talk about in just a second, and we have our own Apex 9 brand for a bunch of different things. CTIconnect is the part of the company I work for. We're the wireless hardware distribution and supply, basically the hardware arm of the organization. Mitotech is our IT network and infrastructure services group. IPPay, most of you probably are aware of. We do credit card payment for the bulk of the wireless ISP industry. iNet Capital is our newest arm. They do leasing, financial services, loans, and that's gentleman running that has been a WISP and has been in the industry for about 25 years. So with that, I'd like to introduce Dan from BLINQ. Dan?
Dan, before I forgot to mention to everyone, if you have any questions, please type them in the Q&A section on your screen, and then we will answer them towards the end. That'll give Dan a chance to go through the webinar and then answer your questions. Thank you. I'm sorry, Dan, go ahead.
Okay, hello folks. My name is Dan Stewart. I'm a senior systems engineer at BLINQ Networks. I've been working with them for a little bit less than a year. My industry experience, I've been in wireless for the last 35 years, anywhere from wireless LANs to high-end point-to-point microwave, worked for Ericsson, got lots of experience under my belt, but I'll tell you right now, LTE can be a very complicated subject that you can get into, and I think my goal today is going to be looking at some of the not less, but more of the topics that come to mind on pretty much any LTE deployment situations. Real quick, BLINQ Networks overview. We were founded in 2010, acquired in 2016. BLINQ Networks holds over 20 patents related to advanced wireless technologies, beamforming, interference management, and the like. Our executive team was actually founded in Redline Communications. So we've got multiple years of experience in developing world-class LTE solutions. So a little word about today. So this is not meant to be a replacement for technical training classes on LTE or CBRS. It's virtually impossible to teach everything that techies need to know in a 45-minute webinar. So if you were expecting to learn everything there was in LTE, you're probably going to be disappointed here. So, you know, my goal is to focus on opportunities and challenges with a focus on capacity and throughput. There's a lot of other LTE performance topics that are not covered here that would be covered in a basic or even advanced LTE training class. So instead of thinking this is a deep dive, let's kind of take this on as a snorkeling expedition, if you get the analogy, I hope. So one of the things that we covered in the previous LTE part 1 was CBRS, but I wanted to cover a little bit more and talk a little bit more about things. So So CBRS CBSDs, what is a CBSD? That stands for Citizens Broadband Radio Service Device. And those are basically considered fixed stations or networks of multiple of those stations that operate on a priority or a general authorized access basis in the CBRS band with Part 96 of the FCC. So one thing that we want to make sure that you understand is that CBRS, while it interlaces with LTE, it's totally independent of the LTE architecture. CBRS rules manage certain aspects of the radio transmission, like transmit power, when it can transmit, the frequency, the specified bandwidth, those kind of things. So it is crucial to operating in the CBRS band 48. So the other thing is that CBRS has an alliance called OnGo, and they promote LTE as the solution for the CBRS band. And quite honestly, the reason why they promote LTE for the CBRS band is because LTE is a standards-based system, which means that anybody can deploy, pull in products from multiple vendors, that sort of thing. So that's really the goal of CBRS in the OnGo standard. So what I want to do is review some of the functional CBRS architectures. The spectrum access system basically manages and assigns spectrum on an as-needed basis by determining available frequencies and a given geographical location and assigning them to the CBSDs. The SAS registers, the SAS is the spectrum access system, it registers and authenticates the identification information and the location of the CBSD. And it enforces these exclusion zones and dynamic protection areas that we spoke about in Part 1, and it manages the interference between Citizens Broadband Radio Services, CBRS, and the incumbent federal operations. So, and finally, it also protects priority access license. Those are the PAL holders from harmful interference from the general authorized access users. So environmental sensing capabilities that you see here, they're used to detect federal frequency, primarily the U.S. Navy on the coastal areas in band 48. The ESCs actually communicate this information up to the SAS, so the SAS can make determinations on CBSDs in the area if there's potential interference, and will tell them to either lower their power or change frequency, that sort of thing. And so it basically monitors this. So domain proxy is a managing intermediary. The domain proxy aggregates all the reports and the protocol messages from the CBSD towards the SAS and vice versa. The element management system, it's an optional device that assists with the management of CBSDs to SAS communications, and it can only be used really with a domain proxy. So the CBSD sensing that you see here, it's optional, and it detects CBSD activity and reports the CBSD activities. Right now, it hasn't even been defined in the CBRS completely, so you don't see much of that happening, but it's essentially CBSD devices, base stations, acting as a sensing tool. So the informing incumbents, let me get that straight, are federal inland radars that inform the SAS when they would like to transmit. And the FCC database that you see here, it refers to the database that's actually controlled by the FCC and the NTIA. They contain information required for the proper operation of the SAS. So CBSDs can communicate with the SAS directly or communicate through a domain proxy. The steps that are involved are pretty simply Number 1, registration. Number 2 is the spectrum inquiry. Number 3 is the grant request. And once all that is cycled through, then once you get the first successful heartbeat, the staff authorizes the CBSD to start radiating. Whoops, I think I flew through a side. Yeah, I did. So in order to operate in the CBRS band, a CPI must certify each installation. Details such as GPS location, antenna gain, elevation, azimuth, that sort of thing, they're all required to be input by the certified professional installer. Just a note there, the CPI certification that's held is personal and not by the employer. So when somebody gets certified as a CPI, they hold that and can use that pretty much anywhere, and the company does not, it is not attached to the company, if that makes sense. The other thing is the CPI doesn't necessarily have to physically install the equipment, but the CPE must certify the installation parameters, and it's solely responsible for the accuracy of the registration data provided to the SAS. Once the CPSD is certified, installed by the CPI, any subsequent CPSD movements, such as antenna, realignment, that sort of thing, has to be reported back by that CPI. And, you know, the FCC and the ONGO have made it very important in that if you put in wrong information or if you allow information to be input under your name, you can be subject to disciplinary or legal actions for any kind of inaccuracies. You could end up being suspended or even terminated with your CPI credentials. So they take this very, very seriously. So once again, the installer does not have to be CPI certified, but the CPI has to certify that installation. They are responsible for all the details of that installation. And if anything's wrong, something was wrong by the installer, if the CPI doesn't know that and they input that information, they could be subject to disciplinary action. That's really the reason why you have certified professionals. Sorry about that, guys. Okay, so what I want to do is talk a little bit about the LTE functional building blocks. LTE was designed primarily to address connectivity between the end user device and the PDN. So the far left with the far right there, right? So to connect the two endpoints, LTE uses 3 different elements: the LTE CPE, the eNode B, and the EPC. So the first, the LTE CPE, it's used to access the network. It needs to operate on the same frequency band as the LTE eNode B that it wants to attach. So many LTE CPEs have the ability to work on different bands in the same way that the LTE base stations, such as the BLINQ Network's FW300i, have the ability to transmit on multiple bands. For CBRS specifically, all links have to utilize band 48 with the frequency, transmit power, and bandwidth being managed by the SAS, the CBRS SAS. The CPE essentially goes through a scanning process to select the proper frequency and network. Once it decides to make a connection attempt, it will use the random access channel over the LTE error interface to place a connectivity request to the EPC. During that attempt, the CPE actually will send to the EPC its MZ and APN configuration, which the EPC will use to confirm and validate the registration. So that's really what's going on here. Once the CPE contacts the SAS and goes through the steps of obtaining the grant to continue transmitting, the CPE actually will go online. If you have questions about that, we can go into more detail, or I can talk to you individually about how the CPE connects to the CBRS and that sort of thing. But these are, again, these are topics that have a lot of subtopic information that we just can't get into with the amount of time that we have. So looking at those three blocks from a BLINQ network standpoint, BLINQ products operate obviously within the LTE standard. You know, standards-based means you don't have to hassle with the proprietary equipment. When it comes to upgrades or adding equipment to an existing private LTE network, all these products will interoperate with very few exceptions. Another example, if you're selling your WISP, again, you're not locked into a specific vendor product, so the ease of the integration into the buyer's private LTE network is much more simplified. Bottom line, it just makes a whole lot more sense to go from a standards base, from a economic consideration. BLINQ products, we've tested our base stations and the CPEs with multiple different types of EPCs, including Cisco, Nokia, Cordis, Telrad, Polaris, and others. Again, it's a standards-based system. Deploying that standard-based system is much more economical than doing a proprietary system. So let's look at the LTE, the EPC key elements. The LTE EPC is kind of the critical control center where everything has to happen here. We're going to kind of talk about these individual elements here. First, the S1. The S1 interface connects the EPC to the eNodeB. It's actually split into two different control planes, the MME and the user plane. So you can see there down at the bottom to the right, you'll see the user data path the data actually goes through versus the control and management that it goes through. The S1 connection is a critical connection, and I try to make sure that people understand the criticality of this connection. If the EPC, as you'll see in a minute, if it's embedded, it's not really a problem because the EPC resides within the eNodeB, and so that connectivity is internal, so it's not much of a problem. But if you go into a centralized EPC, which most large networks do, then the backhaul between the eNodeB and the centralized EPC becomes of critical importance. So you have to make sure that packet loss is as low as it can be there. You don't want to miss heartbeats that are going on between the EPC and the eNodeB. Pretty critical and important. So with regards to the serving gateway, it routes and forwards user data packets while acting as a mobility anchor for the user plane. The packet data network gateway, my tongue's getting twisted. It acts as the interface between the LTE network and other packet data networks. It terminates the SGI interface towards the packet data network. When we're talking about the packet data network, we're really talking about the internet for the most part. But for private LTE, this could be a private LTE network as well. The MME is the control plane entity, and it's the main control node that processes the signaling between the UE and the core network. The main functions that the MME does, they're related more towards bearer management. And again, you can learn more about this in a basic and advanced LTE, but bearer management is something that the MME does. And it manages functions including the establishment of the connection and security associations between the network and the UE. There are security functions that actually go on both within the signaling and the user data planes, right? So when a UE attaches to the network, there's actually a mutual authentication of the UE, and the network is performed between the UE and the MME including the HSS. So we'll talk a little bit about the HSS. The HSS is the home subscriber server. It's the central database of subscriber information. This is where you're going to be putting all your MZ information and all the authentication information. Its role, the HSS, is to communicate with the network and provide subscriber profile and authentication information. The database is actually shared to allow seamless internetworking between the systems. The HSS relays this information to the network using a protocol called Diameter, which communicates with the mobile management entity, the MME. So each one of these interfaces are actually named. Every one of these red dots are actually named, and they have specific functions. And finally, we have the PCRF. The PCRF, it's called the Policy and Charging Rules function. Basically acts as a policy decision point for policy and charging control. It's not typically used much when you're deploying fixed wireless access, but certainly in a mobility standpoint, when you're implementing a private LTE network, you'll see the PCRF come in as a part of the control mechanisms. So we're going to talk a little bit more in depth about the EPC solutions the BLINQ offers, and that's just there's other companies that does this similarly. So it's not specific to BLINQ, but this slide basically explains what the differences are between the embedded EPC and the centralized EPC. So the embedded EPC, it's basically the simplest and most cost-effective deployment model when you're deploying eNodeBs. User traffic, it's broken right out at the eNodeB. That is to say, the PDN is right at the eNodeB. The eNodeB acts as a self-contained network, if you will, in a box, and it can operate autonomously, really. So that's the really cool things about it. It's very fast to deploy, very low cost. The learning curve is very short, not difficult at all. You have to input your MZ information, and away you go. Now, the embedded EPC, they can talk directly to the SAS, just like the other non-embedded EPC solutions from BLINQ. So they can go through a SAS or they can go through a domain proxy. As far as the centralized EPC, the eNodeBs are connected via private network, as you can see in the diagram below on the right. So data offload is actually at the core network instead of at the eNodeB. Okay, that's not good. Sorry, I'm having power problems at my home. That's interesting. Hopefully we'll be able to continue on. I just had a brownout. Are you guys there? Can you hear me?
Yes, we can hear you.
Okay, sorry. I just had a total brownout. So, okay, so BLINQ Networks, we sell and support what's called the Ranius EPC software. BLINQ's again tested with a variety of different EPCs that are LTE standards based. The purpose of using a centralized EPC is if you have large deployments. We're talking about tens or hundreds of eNodeDs, that sort of thing, where you can actually have the ISP hosted or the data center or even cloud deployments for the EPC. It's highly scalable. You can go from 100 users up to 100,000 or more. And the key element difference really between the embedded EPC and the centralized EPC is that it supports mobility. You cannot be mobile between embedded EPC eNodeDs between each other. You can't roam between each other. There's an IP issue that's involved there because it's not supporting mobility simply. So the centralized EPC supports that mobility, and of course BLINQ supports it as well. Okay, so I want to talk a little bit about network optimization. Operators are really burdened with many obstacles in meeting the throughput demands of its customers. Throughput demand is increasing as households have several devices simultaneously streaming video and gaming applications. And quite honestly, that's why many are moving to the standard-based fixed LTE solution. A big bite of the operator's profit margin. Anytime that there's an unanticipated truck roll to a tower to fix a radio problem, that can be a serious issue. Which can cause network optimization problems and capacity issues. The success of any deployment is directly correlated to the radio network design. When you're doing radio planning, if it's executed carefully, the operator can optimize the coverage and the throughput, which in turn provides a greater return on their investment. The topics we're covering today are focused on some very basic configuration and deployment challenges. There's other additional topics such as PCI planning and tuning, patch configuration, radio link timeout timers, KPI formulas, UE radio measurement. There's just an awful lot of things that we just can't squeeze in 45 minutes. So we're going to go ahead and move on. Whoops. So we're going to talk next about coverage. Coverage and capacity, they're interrelated, right? So to improve coverage, you have to sacrifice capacity. Or if you're trying to improve capacity, you have to sacrifice coverage. I mean, there just has to be this trade-off. So LTE, it works really well under non-line of sight conditions, but obstructions between the devices can still affect the signal strength of the link. In case you're wondering, snow and rain may have no effect on the 3.5 gig signal. And you're going to see RF fluctuations as being normal with or without rain. The base station antenna deployment typically needs to be 2 to 3 times higher than the tree canopy for an optimized sector implementation. This minimizes attenuation by optimizing the angle of incidence. So the angle of incidence, if you can see my white arrow here, this is your angle of incidence. And the higher that you go, the fewer trees block the path. Hopefully you all can understand that. So as you get further and further out, obviously more and more trees can, within the line of sight or within the non-line of sight aspect, can potentially cause more issues on the CPE in its ability to connect. You can lower the eNodeD antenna heights and increase the down tilt. You can mitigate against interference issues. So if you've got interference issues coming in, doing down tilt, again, lowering the height, but all of these have specific interactions with the CPEs. The thing that's important to note is the uplink The uplink is the weak link because there's about a 7 dB imbalance comparing to the downlink. Uplink is heavily influenced on the downlink TCP performance simply because of the acknowledged protocol. So in TCP environments, you have to have a good uplink in order to provide good TCP performance, right? So CPEs with poor RF conditions consume much more resource blocks, which will degrade the entire sector. And that's really important that you guys hear this. It's really tempting to take on additional customers on the edge of a cell from a financial position, but it can have a major impact on total cell capacity. I've seen this a lot, been working with LTE deployments and fixed wireless access deployment customers, and they all share that same issue. You know, if we could just get that one customer that's on the outside edge, so we go out there and we find out, yeah, we can get them 20 megabits per second performance, but they don't take into place the issues that will happen on those that are performing really well, because they're now using much more resource blocks, and as a result, the overall throughput of the single sector ends up going down. So that's a very, very common problem. You need to make sure that you heed that issue. I think that's about what we've covered here. SINAR, having the proper SINAR means having a much stronger signal over the noise of the environment. In most cases, wireless links that suffer from poor throughput or instability will typically have the improper SINAR to maintain the stable link. So having a good SINAR is really paramount for proper link stability. I'm going to go on to the next slide here. So a little bit of a word about RF planning tools. So what is RF planning? It's basically the process of assigning frequencies, transmitter locations, and different parameters of the wireless communication system to provide really sufficient coverage and capacity for whatever the service is that you're providing. It really begins with a detailed propagation model that takes into account the characteristics of the base station, the selected antenna, the terrain, the land use, the land clutter, that sort of thing. And digital elevation, one word about this, the digital elevation model, the ground clutter resolution, it's really, really important. Google actually offers in the Google Network Planner a 1 to 2 meter resolution in most areas. That's really decent, but if you start getting into 10-meter resolution, that means that you could literally average out a 10-meter change in elevation that could actually really affect your CPE deployments in the real world. Typical list of RF planning software basically provides things like the signal strength, the signal quality, the best SINAR, the best server areas, uplink and downlink throughput, that sort of thing. So what you're seeing here is the Google Network Planner. This circle is actually a 10-mile radius. I plopped down a couple of, well, not a couple of, two FWI 300Is. Each one covers 180 degrees. So by plopping down two ENO-Ds, we're able to cover 180 degree with 3 different sectors. I basically put this down. I'm not sure exactly where I put this, to be honest with you, but an example of things that Network Planner can do, you can see at the very bottom, it'll actually show you the elevation and anything that's in its path. In this case, there was nothing in its path. That's the reason why it has such a good sign-on. Where you see this, these power indications, anywhere where you see the purple right there is probably not a place that you want to deploy a customer. So it's that sort of thing that is really, really helpful. I'm going to go ahead and move on. Sorry about that. So this is basically showing what the difference is between terrain and ground clutter. We have two different scenarios here where we can compare, location one, this is in Texas and a really flat terrain. The ground clutter is low, very low foliage, kind of an optimum situation. Where location two, this is in Arkansas, where we have hilly terrains and ground clutter is high. Trees and such are considered pretty high. So when we run the propagation analysis, we end up seeing, as you can see, hilly terrains with tall trees can really shrink the coverage area. The dark green areas are coverage with -110 to -120 RSRP. This is what you'd be reading from the CPE standpoint. So the green areas are areas where it's optimal to have a customer deploy, but the light green areas next to it have fallen below the optimum. So you can see, real quickly, what the benefits and the differences are between the terrain, and why really the most important thing that you should be taking out is to have RF propagation maps. RF propagation planning is critical to the environment that you're trying to deploy in. If you try to do it without it, you're going to be flummoxed and not a happy camper. Okay. So we're going to talk real quick about channel planning and frequency reuse. Spectral efficiency, what is that? It refers to the information rate that can be transmitted over a given bandwidth. Frequency reuse or frequency planning, it's a technique of reusing the same frequencies or channels within a communication system to improve capacity and spectral efficiency. So you see over here to the right, this is basically the reference channel plan, if you will, for an FW300i from BLINQ, where we have one eNode B that actually has 3 sectors, and those 3 sectors you see F1, F2, and F1. F1, as an example, could be transmitting on a bandwidth of 20 megahertz and a frequency of 3600. Where F2 is doing a bandwidth of 26 or 20 megahertz and running at 3620. Well, the cool thing about this is you can reuse these frequencies, so you don't have to utilize more frequency than what's needed. You could go to an F1, F2, F3 plan if you wanted to, but it actually makes more sense to be spectral efficient, so you lower the possibility of you being interfered with. So that's really what we're talking about when we're doing this. Frequency reuse is one of the fundamental concepts that involves the partitioning of the RF radiating area into the cells. The frequency reuse plan that we see here, again, it's the standard for which the FW300i operates in. In this configuration, you'd actually utilize 2 eNode Bs or 2 FW300is to do 180 coverage, each one having a 60-degree sector, multiple 60-degree sectors. Okay, there's a lot more that I could talk about this. I think these subjects have subtopics that could go on and on. So I understand if you have questions, feel free to ask them. But realize that, a basic LTE course and advanced LTE course is going to be really helpful for you to take to learn more about this. So I want to talk next about the LTE TDD frame structure. So LTE supports both FDD and TDD. And so what is FDD? So FDD, frequency division duplexing, basically uses separate frequencies for the uplink and downlink. So I can be transmitting on one frequency and receiving on another frequency at the same time. That's basically what FDD is. CBRS for LTE deployments is actually using TDD. So what's TDD? So TDD uses a single frequency shared in domain, shared in the time domain between uplink and downlink, right? So it's constantly switching between downlink and uplink, and that's what you're seeing here on this frame. The D stands for downlink, the S stands for special subframe, which we'll talk about in a minute, and the uplink, or the U, stands for the uplink, right? So there's actually 7 possible frame configurations based on different downlink and uplink ratios. The operator actually chooses a specific TDD configuration depending on the service required. So we're going to look a little bit more into that. So there's an example. That's actually the 7 different possible frame formats, and you can see that the number of downlink and the number of uplink for each one of the frames vary in their ratio, where an example would be, let's use frame format 0, where it's more weighted towards the uplink than it is the downlink. And then you can look at frame format 5, where many more downlinks than there are uplinks. So you can actually decide on which one that you want to support. Now, the specific ones that CBRS supports today are frame format 1 and 2. Okay, and there's a reason for that, and we'll probably talk about that a little bit later. But basically, it's weighted towards the downlink, so the typical internet uses for video streaming, that sort of thing, can be done. And then there's that special subframe. That's that S that you guys saw there. We've already established that TDD mode needs to switch transmission from the downlink to the uplink. The guard period that you see here, which is part of the special subframe, the guard period is required because all the uplink transmissions from the multiple UEs that you see out on the network, all their transmissions need to arrive at basically the same time at the eNode B receiver. So if it's further out, it's going to take longer time to transmit that back. Although it's in nanoseconds, it's really important that this all come together. Timing is just crucial here, right? So a guard period from uplink to downlink, it's not required because the eNode B is the only entity transmitting, right? So the guard period impacts the cell size because it represents how much propagation delay it can compensate for. The guard period has to be large enough to cover the propagation delay of the downlink interferers, so its length determines the maximum supportable cell size. Now, the guard period does not by itself decide the cell size. There are other important parameters like RATch, transmit power, receiver sensitivity, throughput requirements, that all play really a crucial role in deciding what the cell size is, that hopefully we've communicated a little bit to you today. There's actually 9 special subframes in the TDD. Each one has a different number of OFDM signals. The downlink pilot time slot and the uplink pilot time slot, that's where you see that DWPTS there. They're all included as the guard period is included in determining what the total range is, if you will, of the distance of what the cell size would be. So most of the TDD operators, they prefer special subframe 6 and 7. That's typical. The reason why they use this is because the up PTS symbols, they can be utilized for what we're talking about RATCH when you're doing planning and uplink for the SRS signals. Again, some more detail on that, obviously. We can get really deep into this, and I just don't have the time to be more than happy to talk to you offline about it. Okay. So the throughput depends on several things, right? The bandwidth, the channel quality, the network load. When we're talking about the channel bandwidth, CBRS actually operates with a 10 and 20 megahertz channels. The wider the bandwidth, obviously, the higher the throughput. The bandwidth is actually divided into these resource blocks that you heard me talk about. So in a 20 megahertz channel, there's 100 resource blocks. And it's within these resource blocks, as we're transmitting data, that really determines what kind of throughput we can deliver. And of course, the channel quality really impacts the user bit rate, right? So that's why you saw on the previous slide where we were showing the trees and the transmission and how we go down to lower modulation rates as we go further and further out. So that's really important. And then, of course, network load really depends on the available radio resources. So the more subscribers that are active, that are receiving and transmitting, the less resources that are allocated to a given subscriber. In this chart, let's assume that there's a single UE, and let's say they have ideal radio conditions so that we can get peak throughput, which is what we're talking about here. So if you look at the theoretical throughput, when we're looking at column 1 as a baseline, we're seeing 112 megabits download and upload is 11.52. Those are the theoretical limits. This doesn't take into place IP headers, LTE overhead, that sort of thing. So it's going to be a little bit lower than what you see here. But as you can see, what we've done is we've made modifications to things like the TDD configuration, the special subframe configuration that you see in column 2 there, just to show you what the difference is, where we bumped up the upload, but we've lost some down on the downlink, right, as far as throughput. And then if we bump up the uplink modulation to 64 QAM, we get a nice little bump up there in uplink performance. So this chart is basically, showing you the different things that that affect capacity of your network. As we go on, we can go to a 2CC format. CC stands for Common Carrier, in case you're not aware of that. So when we talk about 2CCs, we're using 2 20 megahertz carriers. And with those 2 20 megahertz carriers, and by the way, they don't have to be contiguous. So in a CBRS situation, you could have something at 3620 and then something at 3560, let's say. So it can utilize different bands or different portions of the band to be able to do 2CC. But what you're doing is basically doubling up the capacity, if you will. So on the far right, I basically showed, this is the capacity you can get if you're doing 256 QAM on the downlink and 64 QAM on the up. Now, reality check here, guys, is that typically you're going to always be operating, the CPE is going to be operating in the 64 QAM or the 16 QAM. 256 QAM and the 4 BPSK, you're just not going to get, you're not going to see a whole lot of users there. The lowest order modulation, that's going to be crappy no matter what, because it's going to use a lot of resource blocks. And the reason why you're not going to see a lot of 256 QAM is the signal has to be super, super clean. So we're talking about you have to be fairly close in to get a really high, decent signal with a really good sign-on. Okay. Okay. I think the last topic that we're going to talk about is oversubscription rate. Oversubscription rate, it's basically a calculation, pretty simple calculation. Take the number of subscription plan rates that you have on a single sector, multiply them by the number of users. So in this case, we said, we've got 20 users on a 25 megabit plan. Okay, so that means we've got 500 megabits per second throughput requirement going through a 100 megabit pipe. All right, so in that case, we've got a 5-to-1 ratio. So it really depends on the customer's utilization of the service. Right now, due to the COVID-19 pandemic, you see a lot of wireless network operators are seeing much higher traffic usage due to the stay-at-home isolation rules. And then as a result of that, the user experience becomes less adequate because they've implemented a high oversubscription rate. Any of you guys that are out there that are dealing with that now, I'm sure that you're seeing that situation. So you can see an oversubscription rate of anywhere from 4-to-1 to 10-to-1 for fixed wireless deployments. In private LTE networking for situations that are in IoT, Internet of Things, that sort of thing, you could have a 15-to-1 or even greater because we're talking about throughput requirements that are very minimal. Things like, industrial sensors, industrial automation devices, SCADA, smart metering, that sort of thing. So the oversubscription rate needs to be carefully managed when you're deploying your network. Okay, guys, I know I've taken up a lot of time. I'm going to just spend a whole lot of time here. This is just talking about the BLINQ key technology propositions. Hopefully we'll be able to share a PDF of the PowerPoint so you guys can take a look at this. Probably the strongest thing that I can tell you about BLINQ's technology proposition is that we have a really evolved power control and link adaptations for being on the outside edge. That's where we really shine. We're OnGo certified. We have this full product range. Probably at the core of our FW300i is a number of these cell sectors that you can change and modify just by changing the antenna pattern or the antenna coverage that you have. Again, this is the BLINQ LTE base stations that we've talked about. You can learn more by going out to our website and our NetLiNQ management system. It's a full EMS functionality as REST northbound interfaces. It will have a SAS domain proxy. So it actually does everything that we need it to do to manage the network operations here. So, okay. Wow, I really flew through a lot of this. If you have any questions, please let me know.
There is one question. Yes, there is one question that came in, and I think that's probably all we have time for right now, is why does cellular LTE have so much greater upload capacity? We sometimes see 50 megabits per second upload and 100 plus download over a cell phone. Why don't we see similar upload over the flavor of LTE?
Yeah, so that's a good question. The bottom line is bandwidth that you have to transmit and the modulation rate. There's no, there's nothing that's breaking the physics rules here. It's not magic. It's just what you're capable of doing as far as on the uplink. The uplink is always going to be lower than the downlink, and so yeah. So I would just say that in most of your LTE deployments that you see on the public network for cell sites, they're using FDD technology, which has a lot to do with it. So much cleaner technology, and they have the bandwidth to do so. You got to keep in mind these guys have super clean bandwidth because they have the license. Nobody can transmit or do anything on that frequency without well, they can't. You can't transmit on those frequencies without a license, right? So that has a whole lot to do with it. I think that's about all I can say for that.
Okay. Great, Dan. Thank you so much. That was a wonderful presentation, very informative and educational. And I want to thank everyone for attending our webinar, and be on the lookout for any future webinars coming up here shortly. Okay, thank you. Have a good day, everyone.
Thank you.